This is Jack Jackson, and this is our video on applications of derivatives. But before we get too much farther into this playlist here in this series of videos, I want to go over some pretty important theorems in the theory of calculus, and they form the basis for some important results that we're going to go through later. The first of these that we're going to cover in this video is called Rolle's theorem. Now, Rolle's theorem was first published in 1691 by the French mathematician Michel Rolle. The result is a key tool in proving the mean value theorem, which we'll prove in the next video. And it's also important in the proof of the existence of Taylor series, which is a very important topic in Cal 2. It's going to be important in leading toward L'Hopital's rule, which we're going to cover here in a couple of videos down the road here. So basically what Rolle's theorem says is that for a differentiable function on an interval where the same y values are at the ends of the interval, then there must be at least one point in the interval where the function has a zero derivative and thus has a horizontal tangent line. And that place will be a local extremum. So here's the precise statement of the theorem. It says, let f be a function such that, well, you got three conditions. F is continuous on the closed interval from a to b, f is differentiable on the open interval from a to b, and f of a equals f of b. Now, there exists at least one number, c, in that open interval from a to b, such that f prime of x equals 0. That's what the conclusion is. Now, we're going to prove this now. Now, at least one of the following three cases must hold. But actually, case 2 or case 3 could both hold at the same time. But at least one of these happens. The first case is that f of x is a constant function all the way across from a to b. Now, if that's the case, we can take c to be any number, and every number, between a and b, since the derivative of a constant function is always 0. So that's sort of the easy case. Now, if there's a place where the function goes above what it is on the ends, so f of x is greater than f of a for some x in between a and b, then if it goes up, it's got to reach a highest point because it's got to come back down. And so that must reach some local maximum. The extreme value theorem says if a function is continuous on a closed interval, it must reach a maximum and a minimum on that closed interval. And we know, where does that have to occur? Well, it has to occur either at the endpoints of the interval, or at a place where the derivative is 0, or the place where the derivative is undefined. That's what the extreme value theorem says. But here we know it's not at one of the intervals because there's at least one point that's higher than both ends. So we know that it's not at the endpoints, so it has to be somewhere in between. It has to be somewhere in that open interval from a to b. But we also know the derivative is always defined. See, it's differentiable on the open interval from a to b. So the only place that a maximum could occur is at a place where the derivative is 0. That's a local maximum, a horizontal tangent line there, so the derivative is 0. And the other case is about the same. If the function goes down below the endpoints, then it must have a minimum on the closed interval, and again, that minimum must occur either at the endpoints of the interval, which is not going to happen because it goes at least one place it goes below there, so below the ends, and so that's not where it happens. And we know that it's always differentiable again, so it can't happen at a place where it's not differentiable, so it has to be at a place where the derivative is 0. So that's how Rolle's theorem works. And basically, Rolle's theorem says, notice that if the hypotheses are satisfied, you've got a function, here's an example maybe, where we have it's defined on the closed interval from 0 to 4 here, a to b, and it's continuous, and it's differentiable between there, so we don't have any sharp corners, we don't have any breaks in the graph, and so what happens is there has to be a place in here where the derivative is 0. And so basically, this one has two such places. There's one somewhere around 0.85 here where it reaches a maximum and it has a horizontal tangent line, so the derivative is 0 there. So c equals about roughly 0.85. And then about, what is it? I guess it's about 3.15 or so roughly in here, that there's another c value where the derivative is also 0. So there might be more than one such c value. In this case, there's a one where it goes above and one where it goes below the endpoints, and there's actually two places where the derivative is 0. There might be more than one, but Rolle's theorem says there's at least one. That doesn't tell you exactly where it is. We know where it is in one sense. It's a place where the derivative is 0, but we don't know exactly where that is without calculating the derivative. Now, Rolle's theorem is going to be an important step in proving the mean value theorem, which we'll go over in the next video.